in a row this morning, and the first one is by Doug Arnold from the University of Minnesota. He's going to talk to us about finite element exterior calculus. Please.
Okay, thank you for waking up early. I was thinking a little bit, what's the difference between a regular math seminar talk and a tutorial talk? And well, a regular math seminar talk, somewhat sadly, but we're all used to the fact that much of the time we don't always understand what's going on, and we think that's normal. Tutorial talk's different. It seems like much of the time we don't understand what's going on, but we think it's not normal and we feel guilty about it. So I'm going to try to make this as understandable as possible. And of course the difficulty is then you may run out of time and not cover the material. And I decided that's okay. So if I only get through a third of the material, but you've learned something, then you'll be in a position to read more of the material. So I ask that you interrupt if there's something that's not clear, and let me know if it's going too fast, and give me feedback that I will be able to use to adjust to further lectures. Let me bring this out. So there is a reference which makes it easier. If I don't cover material, you can look it up. So this is a pretty new book from SciAm, good price, but you can download it at that URL, which is on my web page. If your university has a license for SciAm books, so it's not hard to get a hold of. That just came out at the end of 2018, but actually it came from this lecture series, which was 2012 at Brown University, and I circled the 6 people who are actually here at this one also. This was a series of 10 lectures, so that's one reason I'm going to not be able to cover all the material in what's a series of 4 lectures here. I also put down the original sources, which were 2 long papers, one in Actinumeric in 2006 with Rick Falk from Rutgers and Ragnar Winter from Oslo, and another paper in the Bulletin of the AMS, which is quite different material. This was more the discretization part, and this was the Hilbert complex framework in 2010. And these numbers here, well, they're sort of silly because they're citation numbers, which don't mean much, but according to Math SciNet, of the 87,000 papers that they reviewed in 2010, this is the 28th most cited and the 24th most cited. So this is a subject that's taken off somewhat. Okay, so finite element exterior calculus has some prerequisites, and the first 2 parts of the lecture are going to be the 2 prerequisites. One of them is a tiny bit of homological algebra, chain complexes, and the other one is a tiny bit of functional analysis, closed unbounded operators on Hilbert space. And then we put them together into what's called the Hilbert complex. And the idea of this is what we've seen already in talks in this workshop, and the whole theme of the year is that sometimes to get the discretization to work well, it has to reproduce the structures that happen at the continuous level. Well, what do you mean by structure? Well, we've seen examples where a structure meant a Hamiltonian system or a Lie algebra structure or something like that. Here, the Hilbert complex is the structure. The homology is the thing that has to be reproduced, and hopefully that'll become clear as time goes on. By the way, I apologize for going slowly. I didn't apologize to the people who know everything, for whom they're experts, and this is not who this is aimed at. Okay, so homology 101. Let me move this thing out of the way. So what's a chain complex? First of all, let me remind you what a complex is. Complex in mathematics means an object that's built up of several smaller objects with some sort of relationship between them. That's all it means. A chain complex is built up of a sequence of vector spaces, V0, V1, V2. It could even go negative in both directions. And between 2 consecutive vector spaces, there's an operator. And instead of using a letter like T or S for the operator, we use the boundary symbol. So boundary K goes from the kth vector space to the K minus first vector space, and it's a linear operator. And there's only one hypothesis to be a chain complex. If you do the operator twice, 2 operators in a row, you get 0. So there's another way you could view the exact same thing. This is the same thing in different words. You could take the direct sum of all these vector spaces and get one really big vector space, called it V. And then the operator, adding them together, you get one really big operator D that goes from V to V, but that takes V, K into vk minus 1. So it's called a graded operator of degree minus 1. And if you compose it with itself, you get 0. So that's a chain complex. Very simple. There's a lot of terminology that goes along with it. The kth vector space is called the k-chains, which is a strange name, but that's what it's called. You'll see why in a minute. The kth operator is called the kth boundary. So the operators are called the boundary operators. The null space of the boundary operator is called the cycles. The range is called the boundaries. And of course, this hypothesis here tells us that the boundaries at one level are cycles. So the range of this D is contained in the null space of the next D. And that means we can form this space here, which is the quotient of the cycles by the boundaries, and that's called the kth homology space. And that's sort of a key object. What did I forget to say? Anything? Oh, I said it's a bi-infinite sequence of vector spaces. Almost only a finite number of them are 0. So you really only have a finite number of vector spaces, and you stick zeros, and then it's a bi-infinite sequence. Okay, clear? Simple? Anybody lost yet? Okay, I wonder if you're telling the truth. Okay, now I'm going to talk about another kind of complex, totally different, not a chain complex. It's also a complex. It's something made up of smaller things. It's a simplicial complex, and that's a really simple thing. A simplex is k plus 1 points. You take the convex hull, and you get a k-dimensional simplex. And every simplex has faces of every dimension. The points themselves are the 0 faces. Pairs of points give you a one-dimensional simplex, which are the edges or the 1 faces. 3 points gives you a 2-dimensional simplex, which are the facets, etc. And a simplicial complex is simply a finite set of simplices in Rn, such that whenever a simplex is in there, its faces are also in there. And if two simplices meet, they meet in a face. That's it. So it's basically what we call a triangulation in finite elements. But all the faces, the triangulation along with the triangles, the edges, and the vertices. And we don't quite just take the convex hull. We don't forget the order of the points in here. So let's say we've ordered all our vertices for all our simplices in increasing order. Then any one simplex, if it's increasing order, we call it positively oriented, if the vertices are increasing order. If the vertices are some permutation of positively oriented, we call it positively oriented or negatively oriented, according to whether it's an even permutation or an odd permutation. So we have oriented simplexes. Like oriented edges, we distinguish between the one pointing this way and the one pointing this way. Or oriented triangles, there's a right hand and a left hand, positive direction and a negative direction. Okay, what's the relationship between simplicial complexes and chain complexes? Well, every simplicial complex gives birth to a chain complex by the following process. We have to define vector spaces and operators. So the vector spaces is just going to be, the kth vector space is going to have dimension, the number of k-dimensional simplices in the simplicial complex. S is a simplicial complex. These are the k-dimensional simplices it contains. And what we're going to do is we're going to consider each simplex to be a basis element, and we'll take linear combinations of them to get a vector space. Okay, so you can imagine the same thing. Take a piece of graph paper that's been ruled with a lot of fine triangles, draw a pretty picture on it, and then put a 1 in front of every triangle that hits the picture and a 0 in front of every triangle that misses the picture, and then the sum of all those triangles, the sum of the things with 1, represents the picture. If you wanted to get it a little more accurate, if a triangle only hits part of the picture, maybe you'd only put a fraction as a coefficient in front of it. So that's why you have a k-chain that has coefficients that are real numbers. Just linear combinations of the k simplices. Okay, that's half of having a chain complex. It's a vector space for every k. And of course, there's only n plus 1 non-zero ones, because there are 0 simplices, 1 simplices to n, but there are no n plus 1 simplices or negative index simplicity, negative dimension. And then the boundary operator is this operator here. It takes a sum of, it takes a simplex, that's one basis element for the k-chains, and it takes it to a sum of all its faces of dimension k minus 1 with signs in front of them. And those signs are cleverly chosen. So for example, if the original simplex was oriented like this, then when you do its boundary, you'll get its three edges oriented in a consistent manner. So it's the oriented boundary. And that's why the boundary operators in a chain complex are called boundaries, because in this case, they really are boundaries. Okay, and of course it extends from the definition of one simplex to an arbitrary chain by linearity, which is what this says here. Okay, and here's a picture, for example, an edge, its boundary is the difference between its endpoints. If we have three consistently oriented triangles forming a body, then the boundary really is the boundary of the body as consistently oriented edges. Okay, everybody with me? Okay, what's this for? Well, so first of all, how do I get a simplicial complex? Well, the boundary of the boundary is 0. What's the proof? Well, it's obvious, right? You go around a boundary, now it doesn't have any boundary. It cycles all the way around, comes back to where it started. The endpoints cancel out. So it's very easy to prove from that formula that the boundary of a boundary is 0, and so we have a simplicial complex. We start with the n chains. We take their boundaries, we get n minus 1 dimensional chains. We take their boundaries, and all the way down to 1 chains give boundaries that are vertices, and then zeros on either side. And that means it has homology. That means that the cycles, which are the things that have no boundary, the null space of the boundary operator, it contains the boundaries of the higher degree things, and we can form the quotient space, and that quotient space has a dimension, and that's the key topological invariant, the first topological invariant of a body. So imagine Charlie in his talk yesterday had these beautiful pictures of an alloy that had been etched out, the silver had been etched out, and you had a complicated shape of tubes and voids in the remaining gold. So imagine that was given to you in a triangulation, one of these complicated triangulations like Paula had, 1 billion tetrahedra that took 4 months to put into the computer. Your job is to count how many holes there are in that complicated geometric shape. This will give you the way to do it. The Betti numbers are the number of holes of different types. The first Betti number is the number of holes that go through the domain, that you could fly through and go around the domain. The Betti number 2 on a 3-dimensional body is the voids inside a domain, like a basketball has Betti 2 number equal to 1 because there's one opening inside a basketball. Inner tube has Betti number 1 equal to 2 because you can go through it inside or you can go around it outside, and Betti number 2 is equal to 1 because it's hollow in the middle. Betti number 0, the first one, is the number of connected components of a domain. So all that is in this combinatorial object. So again, if you took this complicated surface with lots of holes given to you in a triangulation and you were told, count the holes, well, what you could do is you could form these matrices that represent the boundary operator. What are those? Those are just incident matrices. They give in a triangle, they give a 1 or a minus 1 on the edges according to the incidence of that triangle and its orientation, the incidence of the edge inside the triangle. So you can write down quite easily the matrices that these linear operators represent, rectangular matrices. Then you can take the null space by doing some sort of rank calculation, and you can take the ranges by doing some sort of rank calculation, and then take the quotient space, which is the difference of those. So that's how you use this kind of object to study topology. The picture here is showing 2 cycles, 1 cycles, that is 1 chains which have no boundary, and what they're doing is signaling that there's a hole in the domain, because although they have no boundary, they themselves are not the boundary of some 2-dimensional object. See, if you look at the blue cycle, you might say, well, it closes up on itself, but it's the boundary of a square. But in this body, it's not the boundary of a square because there's a hole that stops you from filling in that square. That's the idea of simplicial homology. Okay, so simplicial homology is a very simple homology formula, and that's where the chain complex was born. Of course, chain complexes could come from many other sources. One more definition, a chain map. Once you introduce an object like a chain complex, you should introduce the mappings on it. A chain map is a map between two different complexes, V with boundary operators and V prime with boundary prime operators. And these are just maps between the kth vector space of one complex to the kth vector space of the other, linear map, in such a way that you have a commutativity. The boundary of F of a chain in the first complex is equal to F of the boundary of that chain. That's called a chain map, and that's the mapping in the category of chain complexes. What can you do with a chain map? Well, from that commutativity, you immediately see that if something is in the null space, that is, something is a boundary is a cycle in VK, so it goes to 0 here, then F of it must go to 0 here, because the boundary of F of it is F of the boundary of it. So a chain map takes cycles into cycles, takes boundaries for a similar argument, it takes boundaries into boundaries, and that means you can define it on the quotient space, cycles mod boundaries, by just applying F to the boundary. You get a new boundary and taking the coset modulo the new cycles. And that's a well-defined map. So a chain map induces a map on homology. So from the fact that you had this chain map, it means that there's a way to map the homology of the top complex into the bottom. A very simple example is where the VKs are subspaces of the VK primes and the F is just inclusion. In that case, you call the first one a subcomplex, and the key condition to have that is the boundary of VK has to be contained in VK minus 1, so you get a complex upstairs. Okay, that's about the definitions that we need for homology, so not so much. But now I have to go to cohomology. So I get a whole nother shot at it. So what is cohomology? Well, that's homology, except the indices go up instead of down. That's all. So a cochain complex is the same thing as a chain complex, except the mappings go from K to K plus 1. And the mappings traditionally are notated with a D rather than with a boundary symbol. Well, that seems incredibly stupid. I mean, there can't be any content to that. And even to make it odder, you use all new terminology. You say co-cycle, co-boundary, co-homology, and so forth. But there's a good reason to do this, and the reason is duality. Suppose you have a linear operator from one vector space to another, then you always have a dual operator that goes from not the first vector space, but its dual space back to the dual space of the first one. So you get D star K plus, boundary star K plus 1 goes from the dual space V star K to the dual space of VK plus 1, V star K plus 1. Of course, the mapping is, well, you know what the mapping is of a dual mapping, I hope. So that means that whenever you have a chain complex, you can dualize all the operators, and we changed the index here, by the way, so it always starts with, we call this dk, so it starts at k and goes up to k plus 1 now. And if you started with a chain complex, this gives you a cochain complex. And so there's, for example, a simplicial cochain complex. If you have a triangulation, a simplicial complex, you have a simplicial chain complex that we saw. So you can dualize it, and you get a simplicial cochain complex. So what is a one cochain? Well, it's a function that assigns to every edge, every one simplex, a number. That's all. It's very similar to a one chain, which is that has a coefficient on every edge, but the difference is these are now functions on the edge, and the big difference is the boundary operator. The boundary operator takes a function on the edge to a function on a triangle, not to something at the vertices like the boundary does. How does it work? Well, if I have a function on the edges, and then I want to invent a function on the triangle, what I do is I take the triangle, I take its boundary, that's 3 edges, I apply the original function to the 3 edges, that gives me a number on the triangle. That's the cochain complex. Okay, so now we have that one example of a chain complex and the corresponding cochain complex. Let me give you a different example, a totally different cochain complex This is the other example that will be very important to us, the de Rham complex. So in 1D, the de Rham complex is a very simple thing. We want to get to calculus somehow. Well, what's calculus? Differential calculus is derivatives. So we write down the derivative as an operator. We take a vector, we take a function space, and we take the derivative operator on it. So we have many choices of function space we could choose, C infinity, C1, H1, whatever. Let's take C infinity. We take the derivative operator. Omega here is a one-dimensional domain, an interval. So this is just the mapping from functions on an interval to their derivatives. And we extend that to a complex by making it all zeros. Any complex with only two non-zero spaces is a complex, because if you compose two of them, you get zero. That's the de Rham complex in 1D. Pretty simple. De Rham complex in 2D is a little more interesting. You take a function on a two-dimensional domain, you take its gradient, so that now that's a vector-valued function on the domain. And for the second operator, we need an operator that takes a vector-valued function to a scalar-valued function, and what we take is the scalar curl, which I write as the root. So that's du2 dx1 minus du1 dx2. And if you apply that to the gradient, of course, you get zero. So that's a complex. So the key fact we've built in there is that the curl of the gradient is zero. That leads us to a complex. And I'm going to number these spaces. So this is the zero space, the one space, and the two space, increasing indices. So I should call this a cochain complex. It's totally different from the previous complexes we saw because the vector spaces are infinite dimensional now. They're function spaces. In 3D, you get maybe the most interesting case from one that's for a lot of applications, which is you start with scalar functions. You take their gradients at the zero level to get vector-valued functions at the one level. Then you take a vector-valued function at the one level, you take its curl, you get another vector-valued function at the two level, and the curl of the gradient is zero. And you take that second vector-valued function at the two level, and you take its divergence, and you get a scalar-valued function at the three level. And the divergence of the curl is also zero. So we've put those two calculus identities together, and we extend this by zeros, and that gives us a cochain complex. That's the de Rham complex in 3 dimensions. And then you see, okay, so it's a strong belief of mine that if you're doing something in 2 dimensions and 3 dimensions, and you couldn't explain how you would do it in n dimensions, you're probably doing it wrong in 2 dimensions and 3 dimensions. So this should be an n-dimensional thing. So what should it be? Grad root, grad curl div, what's the next one? Grad what? Well, there's not names for all those operators, but they're all defined in a uniform way, and we'll get to this later. They're called differential forms, and the exterior derivative is these grads, curls, and divs. So in ND, there's a space called lambda 0 of omega, which is nothing other than C infinity omega. And there's an operator called the exterior derivative, which takes you to lambda 1, and lambda 1 is nothing other than Rn valued functions, and the first exterior derivative, d super 0, I didn't write the 0 here, d super 0 is just the gradient. There's another operator here, I'll tell you what it is. You take a vector field, you take its gradient, but then you only keep the skew symmetric part of that. That's the first exterior derivative. So that would get you from vector valued functions to skew matrix valued functions. That's the second exterior derivative. And there's a way to do this all the way to the end. So there's a de Rham complex in ND. And actually, we won't get to that in this course, but all this works perfectly well on an arbitrary manifold. There's a de Rham complex on any manifold, without a metric, without an embedding in Euclidean space, and so forth. So this includes this first D is the surface gradient on a manifold that Charlie was talking about. Okay, in ND, the definition of the general K, differential K forms, lambda K of omega, differential K forms, is they're functions on omega whose values are in what I call alt KRN. And the precise definition of alt KRN is it's a K linear form. It's a form in K vectors, linear in each of them, and totally skew symmetric. If you interchange 2 of the vectors, you get the negative of what you originally had. So for example, alt 2 of Rn is a bilinear form on Rn. It takes 2 vectors and gives you a number. and it does it in such a way that if you reverse the two vectors, you get the negative. So if you wrote it as a matrix, it would be a skew-symmetric matrix. Well, KRN is a skew-symmetric n by n by n k times tensor. Okay? Little pause, any questions? Okay, what can you do with these differential forms in the de Rham complex? Well, as I say, there's this exterior derivative that maps one space into the next. A remarkable thing is that it's incredibly easy to integrate a differential form. If V is a differential K form, and F is a K-dimensional chain, so now I'm connecting chains with differential forms. If V is a K form and F is a K-dimensional chain, then the integral of V over F is a number that's amazingly easy to define. There are no measures, there are no metrics. It's defined as following. Let me explain first how you would define the integral of a one form. Let me do this a little higher. V is a one form, which means at every point x, V of x is a bilinear form that takes two vectors, let's say w and y, and gives you a number. That's what a one form is, right? For every x in the domain, and for w and y in Rn, Vx, Wy is a number, bilinear in w and y, and if you reverse w and y, you change the sign. This is a two form. But okay, so let's do a one form first. I'll do a two form next on the slides. So that I only have one w, and now that's a one form. Okay, and the alternating is trivial when there's only one thing. It doesn't mean anything. Okay, now what I want to do is I have a curve, that's my f, and I have v on it, which at every point takes a vector and gives you a number, and I want to come up with a number out of the two, the integral of f of v. Okay, well, a curve is basically a bunch of vectors lined end to end, well, approximately. So I approximate my curve by a bunch of little tiny tangent vectors. I take one of these little tiny tangent vectors, it starts at a point x, and it's a vector w, and the integral over that of v is simply v at x plus w minus, sorry, what am I doing here? I take v, I evaluate it at x, and I stick in w. Sorry. Right? V is something that you can evaluate at one point and stick in a vector and get a number. And that's the number that I would apply to this. So this is the sum of all these over the different x0, x1. That's all. So maybe another picture for two. Suppose I have a surface. A surface is very well approximated by a bunch of parallelograms. A parallelogram is given by one point and two vectors emanating from that point. So I take the differential two form, I evaluate it at that point, plug in the two vectors, get a number, add it up over all the parallelograms, and let the mesh of parallelograms get finer and finer. That's the integral of a differential form. That's why a K form can be integrated over a K-dimensional body. And the highlight of exterior calculus is Stokes' theorem. It's the right setting to prove Stokes' theorem. All the forms of Stokes' theorem that you know are basically this theorem here, which looks so beautiful because to get the integral of du, the exterior derivative of a differential form, K form over a K chain, you just slide the d down in front of the c, you can integrate the differential form over the boundary of the K chain. So suppose u is a K chain, du is a K plus 1 chain, c is a K plus 1, sorry, u is a K form, du is a K plus 1 form, c is a K plus 1 chain, that integral is a number, was a K form, the boundary of c is a K chain, so that's a number and those are equal. That's Stokes' theorem. And when applied back in the situation on the top of the board, all the famous Stokes theorems come out of this. The integral of the divergence is the normal component and so forth. We didn't talk about, well, let me stop there. Any questions on that? Okay, and again, Stokes' theorem works on any smooth manifold. So Charlie proved that by embedding his manifolds in a higher dimensional space and using projections onto the tangent space and so forth, but you don't need a higher dimensional space. It's very intrinsic, and this is the intrinsic theory. Okay, and let me cap this off with one of the great theorems of cohomology theory, the de Rham theorem. So we had these two complexes, two examples of a cochain complex. The de Rham cochain complex with these infinite dimensional function spaces and the exterior derivatives, grad, curls, divs, etc. And we had the simplicial cochain complex associated to a simplicial complex S, where the spaces are the dual spaces of the K-chains. And there's a natural map connecting these two very different objects, this big infinite dimensional object and this simplicial object, a combinatorial finite dimensional object. Given any differential K form, I wanted to find a simplicial cochain. So what's a simplicial cochain? Remember, it's a function on K-dimensional chains. Okay, so given a U, I have to come up with a function that takes a K-dimensional chain and pops out a number. And here's that function. Take the chain and integrate U over it. So the integral of a K form over a K chain is a number. So integrating a U over something is a function from chains to numbers, so it's a cochain. So here's a map from differential forms to simplicial cochains. That's called the de Rham map. Here I've drawn it in a diagram. There's the de Rham complex. There's the simplicial cochain complex with the co-boundary operators, which are the dual of the boundary operators. And down here I put the de Rham map. And now you write out to see if this is a chain map. You write out the definition of chain map to see whether the co-boundary of the de Rham map of a differential K form is the same thing as the de Rham map of the exterior derivative of that K form. You write that out, and that is the statement of Stokes' theorem. Stokes' theorem is exactly the statement that the de Rham map is a chain map, that this diagram commutes. It's beautiful, but very simple. And since this diagram commutes, we have an induced map on homology. So now we have this situation where we have the cohomology of these de Rham complexes of infinite dimensional function spaces, and we have a way to map those into the cohomology, which is some sort of combinatorial object of these finite dimensional simplicial cochain things. And de Rham's theorem says that's an isomorphism. So what's that saying to us? That's saying if you want to compute the number of holes in some complex body, okay, you could take a triangulation and count ranks and so forth, but you don't need a triangulation. You can instead look at the ranges of simple differential operators like divergences and curls and the null spaces of those operators. So for example, suppose you have this body here and you want to see there's a hole in that. We know how you could do that if you triangulate it. But instead now, I'm going to look for functions whose curl is 0, but which are not the gradient of some other function. And there's one hole in that, so there should be a one-dimensional space, essentially one function and its multiples that satisfy this condition. And I've drawn a picture of that vector field. So this U is a vector field, grad theta. Theta is the cylindrical angle variable. But I think of it as a one form, because a one form is a function, is a vector field essentially. And it's not really the gradient of a function, because theta is not a function. Theta is multi-valued. There's no way to define a function whose gradient is this. So this is not the gradient of a function, despite the fact that it looks like one. But its curl is nevertheless 0, because locally it's the gradient of a function. So this is a function whose curl is 0, but it's not a gradient. That signals there's a hole in the domain. If there were not a hole in the domain, I wouldn't be able to define grad theta. And if the domain were cut so that the hole wasn't a hole, it was just a a channel into the domain, then I could define theta so it was a gradient. So in either case, there'd be no homology. But there's a homology because there's a hole. And Durant's theorem says exactly like that. There's one hole, means there's going to be one function like this. This is a different situation. This is a vector field too, but this is a vector field that's a two form. And for a vector field that's a two form, that means that we should be taking its divergent. So what I claim is that this vector field has cohomology in the sense that d of it is 0, but d for a two form is the divergence, not the curl. It's probably a good idea to put up the Durant complex in 3D here. So we have C infinity functions, we have the gradient, that's 0 forms to one forms, then we have vector fields, then we have vector fields again, and this is the curl, that's our one exterior derivative, and then we have the divergence and scalars again. So now we're over here. We have a vector field over here, and I claim that the divergence of this vector field is 0. Well, the divergence of grad 1 over r is Laplacian 1 over r. That's 1 over r is the Green's function, so it's harmonic everywhere except in the middle, and there's a hole in the middle that's not there. So this is divergence free. But it's not a curl. Well, actually, it's very easy to show that this is orthogonal to the curl of anything because it's a gradient and because the tangential components are 0, so you can integrate by parts. So this is something that's divergence free but not a curl. That signals there's a three-dimensional hole, a void inside the domain. So this has Betty 1, not 0, because you a tunnel through the domain. This is Betty 2, not 0, because there's a hole in the domain. This domain is the whole sphere hollowed out. I'm only drawing half the sphere. Okay? So two totally different ways to get at the holes, the topology of domain. The cohomology of the Durant complex and the cohomology of the simplicial complex, and Durant's theorem says they're the same. By the way, so one of the great things about exterior calculus is it takes vector fields and it says, well, there's really two different kinds of vector fields. They're very different. One has to do with integration over lines and line integrals and things like that. The other has to do with integrals over areas, surface integrals. And the first person to notice this was maybe Maxwell, who has a statement in his book where he says exactly like that. Vector quantities are of two types, one with reference to lines and one with reference to areas. Okay, that's homology 101. Now, any questions? Next thing is some functional analysis. It's just going to be Hilbert spaces, but not bounded operators. I assume everybody's pretty familiar with bounded operators on Hilbert spaces. Unbounded operators, well, the key thing with an unbounded operator is it can't be defined everywhere, or it's not so interesting. So I'm going to take two Hilbert spaces, x and y, and I'm going to take a linear operator that's not defined on the whole space x, but on some subspace called the domain of t into y. And the domain of t is usually not a closed subspace of x. It may be all of x, or it may be a dense subspace. Then when you ask what is an example of a bounded operator, actually the first unbounded operator, the first example is a bounded operator, so it's bad terminology. You should call it a not necessarily bounded operator. And we're usually interested in the case where it's densely defined, so the closure of the domain is the whole space. And so the best example to keep in mind is take L2 functions and take their gradients, which takes you to L2 vector fields. Well, not everywhere. It's only defined for things in H1, so when you take the gradient, you do get an L2 vector field. So L2 with domain being H1 and the operator being the gradient is a typical unbounded operator on L2. I don't have to take H1. I could take something else. I could take H01, for example. That's a different unbounded operator because it has a different domain, even though it has the same formula gradient. And you can do things, you can add them, you can compose them if you choose the domains carefully, and so forth. An important concept is the graph norm and the associated inner product. On the domain, there's a norm. Well, of course, there's the usual norm from the Hilbert space X, but there's another norm where you take the usual norm and you add to it the y norm of T of V. That's called the graph norm. That's another Hilbert norm. And there's null spaces, ranges, the graph, etc. Okay, important definition is an operator is closed. Closed is the substitute for bounded. Many properties of bounded operators extend to unbounded operators if the unbounded operator is closed. The definition of an unbounded operator being closed is that the graph of the operator, the set of all x comma t of x, which is a subspace of x cross y, is a closed subspace of x cross y. Remember the closed graph theorem that says an operator that's defined on all of x is bounded if and only if its graph is closed. And so this extends bounded operators to ones that are not defined everywhere. And here are some important properties that show you that a closed unbounded operator is sort of similar to a bounded operator. Its null space is always closed. If it's bounded below in the sense that the norm of Tx is greater than some positive constant times the norm of x, that happens if and only if it's 1-to-1 and has a closed range. This property of having a closed range is very important. We'll see it a lot. And one way you can get a closed range is take the range of a closed operator, and if it's finite codimensional, then the range is closed. So these are not difficult theorems to prove that come direct from the definitions. That'll be very useful to us. I'm going to skip all of this. Don't even bother to read it. No, I'm not. I'm sorry. Suppose you have a densely defined unbounded operator. So this is a key operation on it. I can't skip this. If you have an unbounded operator and its domain is dense, you can define a dual of it, which is an operator going the other direction. So the original operator went from x to y. T star will go from y to x. Not from the dual space of y, but from y itself to x. And it's defined by T star of w of v is wt of v. And if there exists a T star w with this property, that's when v is in the domain, that's when w is in the domain of T star. So I don't think I'll take the time, I'm sorry, I'll rush over this in the definition, but this is the definition. It's fairly straightforward to define the adjoint of an unbounded operator. The adjoint of an unbounded operator is always a closed operator, and most important, if T is a closed densely defined operator, the kind of operator we'll be dealing with, then its adjoint is also a closed densely defined operator. So every closed densely defined operator, like the gradient from L2 to L2 vector fields, has an adjoint, which will turn out to be a divergence going the other way. The adjoint of the adjoint is the original operator, if it's a closed operator. And you have this duality, which is similar to what you have for bounded operators. The closure of the range of T is the null space of T star. The closure of the range of T star, sorry, the orthogonal complement of the range of T is the null space of T star. And the orthogonal complement of the range of T star is the null space of T. And then if you just take orthogonal complements on both sides, well, if range of T is closed, you get back to range of T. Otherwise, you get the closure of the range of T, that's here, is the orthogonal complement of the null space of T star, and vice versa. So you have a duality between the range and the null space of the adjoint, except that you have to close the range.
Excuse me, so why is the dual operator only defined for densely defined operators?
Because if, very good question. If the domain of T wasn't dense here, this wouldn't succeed in uniquely defining T star W. You could take anything that was orthogonal to V and get another candidate for T star W. The density makes it unique. Good question. Anything else? And a very important theorem from calculus that goes over from the bounded case to the closed case is a closed densely defined operator has closed range if and only if its adjoint also has closed range. I won't prove that. And finally, let's bring this down to earth by taking some specific operators. If we think of these operators acting on L2 functions, the gradient on L2 function with domain being H1, its adjoint is the divergence on L2 vector fields, or the negative divergence on L2 vector fields, with adjoint being H01. So you can prove that from the definition of Sobolev spaces and using analysis. The adjoint of the curl operator, well, how do I think of the curl operator as an unbounded operator on L2? Its domain is H curl, everything in L2 whose curl is also in L2. Then the curl maps L2, or a domain inside it, onto L2 vectors. And its adjoint is the curl again. Curl adjoint is curl, but with a different domain, with the H0 curl, the ones whose tangential component vanishes on the boundary. And the adjoint of div with domain H div is the negative of the gradient with domain H01. So it's a fairly simple picture, and it goes over to the n-dimensional case. Okay, so now we've had homology 101 and unbounded operators 101, and we stick them together in the structure that finite element exterior calculus is about, which is called a Hilbert complex. So we defined Hilbert complex in this paper in the bulletin, and we called it a Hilbert complex, but while we were writing the paper, then I started Googling. I found there was already something in the literature called a Hilbert complex, and was the exact same thing. So it's a very natural concept. So the concept goes back to Bruning and Lesch, were the people who first defined the Hilbert complex.
When was this?
What's it? What is it?
Was it 92?
I believe Ari. He says 92. I mean, it wasn't a real long time ago. Ragnar met Bruning at a conference fairly recently. So what is it? It's a sequence of Hilbert spaces, WK, and the operators between them are not bounded operators. They're closed, densely defined linear operators, DK. So that means each of them has a domain. It's not on all of WK, but on a domain from WK into WK plus 1. And of course, the range of one of them has to be in the null space of the next. Not only in the domain, but it has to go to 0. And we use as a notation VK for the domain of DK. So that's a Hilbert space. And it has the graph norm with the graph norm. The fact that this is complete is just a statement that DK is a closed operator. So that means we get a chain complex by taking the domain spaces, and then D is a bounded operator. These are Hilbert spaces with the graph norm, and then D is a bounded operator. So the full Hilbert complex of unbounded operators gives rise to this domain complex with bounded operators, but this has more information because this also has the W norm, and from this you can't deduce the W norm. This only has the V norm. So these spaces have two norms on them, the W norm and the bigger norm, the V norm. And you get bounded operators if you use the bigger norm, and we consider both things as part of the Hilbert complex. Okay, so this is two things. It's functional analysis, it's Hilbert spaces and closed operators, and it's homology. It's a bunch of vector spaces with linear operators, so it's a cochain complex. It has cocycles, co-boundaries, co-homology. And the one important definition, we call it closed, not if the operators are closed, they are by definition closed, but if their ranges are closed. If each of the D's has closed range in the following W, that's called the closed Hilbert complex. If the ranges are actually finite dimensional inside the null space of the next space, it's called a Fredholm complex. And if we use that theorem that says if the range of a closed operator is finite codimensional, then it's a closed range, we get that a Fredholm complex is a closed Hilbert complex. That's how we're going to prove most Hilbert complexes are closed. Okay, what can you do with a Hilbert complex? Well, it's a cochain complex. You can take its dual and get a chain complex. So with every Hilbert complex, there's a dual Hilbert complex. And I indicate this still with a D, but with a star, and the K becomes a subscript. That goes back the other way. It still goes, the dual goes from the range space to the original space, so D goes from WK minus 1 to WK, D star goes from WK to WK minus 1, but it has a different domain. It's the domain of the dual operator. We defined the domain of the adjoint. And it's easy to see that this is a complex, that is the range of one D star is contained in the null space of the next D star, and so we get a Hilbert chain complex. So, and it's closed, it has closed ranges if the original complex is closed because of the closed range theorem. Okay, so now I claim that if you have a closed Hilbert complex, you get lots of wonderful things. You get all the things we need to do analysis of PDE in this context. So the first thing you get is the notion of a harmonic form. So we have the cohomology, which is the fields whose exterior derivative is 0 mod the exterior derivative of lower dimensional fields, right? Of lower dimensional fields, K forms. In the Hilbert complex context, you can recognize this quotient space as functions. If you're in a Hilbert space and you have a closed subspace, you don't have to talk about the quotient space, X mod R. We have a Hilbert space X, and we have a closed subspace, let's say B, for boundaries, or a Hilbert space Z even, let's call it Z. So this is just a Hilbert space, this is a closed subspace. We could talk about Z mod B, but this is naturally isomorphic to the orthogonal complement of B inside Z. Right, that you can use the inner product to do that. So with Hilbert spaces, we never have to talk about cohomology. Instead, we can talk about harmonic forms. You take the Hilbert space Z, the null space of D, and you take the orthogonal complement of the boundaries inside that space. So it's the orthogonal complement of the co-boundaries inside the co-cycles. That is called the harmonic forms. And then we can use duality that says the orthogonal complement of the range is the null space of the adjoint. So the harmonic forms are really just the null space of D intersect the null space of D star. There I've written it out. They're everything in the domain of D and the domain of D star, such that D takes them to 0 and D star takes them to 0. And here I've just drawn a picture to remind you what orthogonal complement means. If this is the space B, say, it's some subspace of the big space Z, then the cosets Z mod B, that's everything that's, if I take Z0, everything in the same coset is just Z0 plus an element of B. That's a space parallel to the space B. And so the cosets are these parallel spaces, parallel to B. And now every one of those cosets has a smallest element. That smallest element is the harmonic form. So the harmonic form represents the cosets by taking the orthogonal complement of B inside Z. Let's skip this. Now you can do, let's do this on the board. Now you can do a very simple calculation that's extremely powerful. Let's take our Hilbert space W. Well, I can break it up into the null space of D and the orthogonal sum with the orthogonal complement of the null space of Z. So this is just use the fact that this is a closed subspace, so it has an orthogonal complement, and together they give you the whole space. Okay. On the other hand, this Z contains the boundaries. The boundaries, that's the key idea of a complex. The boundaries are contained in the co-boundaries are contained in the co-cycles. And this B is a closed subspace, well, because I'm assuming I have a closed Hilbert complex, so the ranges are closed. So I can do the same thing. Z breaks up into B plus the orthogonal complement of B inside Z. But what's the orthogonal complement of B inside Z? That's the definition of the harmonic forms, the orthogonal complement of B inside Z. So here I put the harmonic forms. And this is just breaking up the cycles. And I still have this piece. And if I want, I can use duality on this that says the orthogonal complement of the null space of D is the same as the range of D star, so I can call this B star. So what have I done? I've said whenever you have a Hilbert complex, you can take the base spaces WK and break them into three pieces. The range of the Ds, the range of the D stars, and the harmonic form. That's an orthogonal decomposition. So one example of that would be to say you could take every vector field and you could write it as a gradient plus a curl plus a finite dimensional space of harmonic forms whose dimension is the number of holes through the domain. That's, of course, the Hodge decomposition. It's a trivial result in this setup, and it works for every Hilbert complex. Very powerful. Another incredibly useful result that comes for every closed Hilbert complex is... What's that?
Just a few minutes left of your time.
Okay, I get, yes, just a few minutes. 3.5, right?
Something like that.
If we take any Hilbert complex, it has associated with it a Poincare inequality, which in the simplest case of the de Rham complex and the first operator being gradient, it's our usual Poincare inequality that the L2 norm is bounded by the gradient of L2 norm of the gradient for any function that's orthogonal to constants. The general result is that if you have a function that's orthogonal to the null space of D, then it's bounded by the norm of dz with a constant independent of z called a Poincare constant. Many things come out of that. For example, Korn's inequality is an example of this. And exterior calculus is a way to prove Korn's inequality. So, since I'm running out of time, as was just pointed out, let me just point out where we're going on this. We're going to deal with PDEs for which this Hilbert complex is lying in the background. In the simplest case, it's the de Rham complex. We'll also see other complexes for different PDEs. When there is a Hilbert complex in the background of a PDE, there's all sorts of structure to the PDE. In particular, there's a Hodge decomposition and there's a Poincare inequality. What we're going to do is discretize that PDE in such a way that there's a discrete Hilbert complex, a subcomplex. Since there's a discrete Hilbert complex, there's a discrete Hodge inequality and there's a discrete Poincare inequality. Those are the things you need to analyze the numerical method. Let's see what I have on the next page. So that gets us to the PDEs. I think I will stop here.